Like you said, I'm John Bruckman. I'm from Monmouth College. This is an NSF-sponsored REU. I'm working with Dr. Robert Kay. And I'll be talking to you about collective structure in arsenic activity. All right, so first, there's some motivation here for going into this region and studying these nuclei. I guess first I should point out that Wild West here, in quotes, refers to the area that we're working with. It's the relative to the line of stability in the chart of nuclides. It's a proton-rich area, and so we're off on the left. It's lovingly referred to as the Wild West. So, yeah. These particles are ideal for studying single particle behavior versus collective particle behavior. And what that means is the angular momentum of the nuclei mostly due to these two particles, or a particle, or whatever, or the entire structure of the nuclei. Are they acting together or separate from each other? Over here on the right, you see this level scheme. And with odd nuclei, what you end up having is one neutron and one proton up here by themselves in some top level. For me, particularly, it's up in this region. And they're unpaired. And so what that means is you have two separate particles contributing to single particle behavior. Like I said, the protons and the neutrons fill the same shells. They fill them independent of each other usually. And these nuclei, because they exhibit both single and collective behavior, is why they're so ideal for the study. And just so you know that the collective behavior is very similar to the classical rigid body rotor, classical thing. So anyway, background. I'm talking about evolution of collective structure here. So I really want to know, how does arsenic 70 fit into the area around it in the chart of nuclides? And so we go up to the next odd arsenic nuclei, and that's arsenic 72. For those of you who haven't seen a level scheme before, which I don't know how many of you haven't, but we have a mathematician in the room at least, so there's one person. You'll notice that there are these sort of integer values here with pluses and minuses. They are the spin and parity values. They're just quantum numbers. You have these lines here, and they are labeled with values. Those are the energy levels, so at what energy is that line. And then these arrows here are just transitions. So when it decays down, it'll emit a gamma ray with that energy. So for arsenic 72, we have this sort of busy structure here at lower energies. And as you go up, you start to get these very predictable bands. This is indicative and actually very traditional in these odd nuclei in this region. And it's indicative of collective behavior at these higher energies and single particle behavior at these lower energies. It's the first indication of said behavior. So we move down an odd nuclei to arsenic 68, and we start to see that, well, immediately it's not at all the same. The entire thing down here is very busy, like before, but we don't really get regular patterns forming as we start moving up. And you have a few coming here, but they really aren't enough to say that it's collective. It's not behaving in the exact same way. You don't have these bands going up right next to each other with the crossing between them. It's not exactly the same. And so we would say that this is probably dominated by single particle behavior. And then we get to the nucleus that I actually did some analysis with. And we see that we have sort of these bands forming here, but it gets kind of busy toward the bottom. And there are some gaps in this level structure. It's not completely studied as of the publication of this level scheme. And so we don't know, given this, whether or not it would be single particle or collective. And just so you're aware, this right here is just a study that was done on just the lower energies. And so that's how busy down here can be. And typically they're all like that. It's just harder to display on these graphs. And so, yeah, just so you're aware that single particle behavior gets really busy. All right, so I was doing mostly data analysis, and the data that I was analyzing came from an experiment at Florida State University. There was a beam of sodium-23, negatively charged, accelerated to a kinetic energy of approximately 80 MeV, and it was shot at target nuclei of iron 54. It was a thick target, which means that there was no nuclei coming out of the back of the target, basically. When sodium strikes the iron, you have a fusion reaction. From there, you can either have fast fission or the compound forming, rubidium-77. Once the compound forms, if it forms, you have a lot of angular momentum given to that compound nuclei. And so what's going to happen is it's going to be spinning extremely fast and spitting off particles. For arsenic-70 to be formed, it's going to spit off an alpha particle, which is 2 protons and 2 neutrons, and also another 2 protons and a neutron. So that's the alpha plus 2pn channel for this decay. Once it decays in arsenic-70, it's going to give it off quite a bit of energy there. And so in order to decay further to the ground state, or to a state where it's no longer in a way where it wants to lose energy, it's going to be emitting those gamma rays, those transition arrows that I showed you. And from there, it's in this high excited state, so it's in one of those higher bands. It's going to move down to the ground state. All right, so here's a quick picture of the detector array. There are 10 detectors, 4 clover detectors, which are just 4 crystals embedded into one detector, and several non-clover, which are just the regular detectors. And they're sort of in this nice, complicated-looking array. They're taking gamma rays in coincidence. Coincidence means that when you have a gamma ray strike one of the detectors, it's only going to record it if another gamma ray strikes one of the other detectors. And that has to happen within a 100 nanosecond time window. If it doesn't happen, then we throw out that gamma ray. This is just a way to sort of reduce the noise, reduce the background, things like that as you're going through the experiment. All right, so now we're going to get to some analysis. The first thing we had to do was sort of confirm whether or not the literature published was accurate enough to go by, to base some of our assumptions on. And so right here is a sample spectra of what you would get doing this experiment. And I've labeled some of the peaks that you would see in here, namely the ones with the asterisks. And so, going through, I actually confirmed all these levels, and I'm not going to, show you all the spectra for that, but just so you know that all of the levels that were in that previously published one were basically confirmed. Then, going along the same method, looking at things in coincidence with each other again, we had this hole that we wanted to fill. And so if we could fill this and get this nice band structure, then we would say, all right, well, this is probably behaving collectively. Getting gamma rays in coincidence with this 1274, I was able to work my way down. And I'm not displaying that because it was kind of noisy, but over here on the left, you see this sample spectra, which was actually in coincidence with the 321 and the 302, as well as the 81 right here. And what I'm doing is summing those together just to get some statistics so that you can see those peaks forming. And so yeah, these are the new level states that were formed. They were negative parity. Moving forward, we're sort of like, all right, well, it looks like it's behaving collectively, but we have to do some computation and sort of work on just how collectively it's behaving. So we do what's known as signature splitting. It's basically just the normalized energy differences between adjacent states. So you have 9 plus, 8 plus, 7 plus. Those are adjacent states. And if you see these sort of zigzagging patterns here between the positive parity, you can, that's sort of conducive to odd nuclei systematics and an indicator of collective behavior. And we're seeing these patterns emerging for all 3 of these positive parity states. And there were some negative parity similarities as well, but those are harder to predict due to convoluted wave equations in the theory. It's just harder to work with at a theoretical level. You don't always have to get those nice zigzag patterns. All right, another calculation that we did was doing the kinematic moment of inertia. This is sort of the quantum analogy to the classic rigid rotor value, or problem. And so what you have here is this dashed line represents what the rigid rotor value would be were a classical system. That is sort of the predicted value. And if you have, as angular momentum increases, if you have these things approaching that line, then we sort of see, all right, well, it's behaving collectively at higher energies. All right, to summarize, found the new negative parity band. Arsenic 78 exhibits strong collective behavior at higher energies and single particle behavior at lower energies. And collectivity seems to increase with neutron number of for the Z equals 33 isotopes.
Questions for the speaker? What were you just working on?
Oh, we just actually spent a week at Argonne working on a rather convoluted experiment dealing with high energy isomers in silver 94. So it was it's kind of a big deal. It's a really hard experiment to do. Probably one of the hardest you can design right now. And it's pretty exciting stuff. So hopefully we'll see those nice level schemes for the higher isomers and things.
Question?
Yes.
Back to the graph where you had the gap filling in the red. Yeah, and then the one before it. So is that just relative to each other at a different intensity? Are those peaks generally the same width when you get the spectra in? Or
Well, so you have sort of I mean, these are real machines, right? And so what happens is at higher energies you tend to have wider peaks just because of efficiency in the detectors. However, if you sort of calibrate detector efficiencies and things, you can do all sorts of measurements with the width of the peak, whether it's sort of shifted left, shifted right, things like that. And they aren't typically exactly the same width. So, I mean, these seem like, you know, pretty straight peaks here, but if you zoom in and you do a lot of calculations with them and curve fitting and things, they're not exactly the same.
Are you asking about the width of the arrows or the width of the peaks in the gamma spectrum? Oh, okay. Yeah, they're wider too because of Doppler shift effects. So those gamma rays that you see at the top of the scheme, the nucleus is actually recoiling in the target when those are emitted. And so there's a Doppler shift in the measured energies, which tends to widen peaks.
Okay, let's thank the speaker again.